Okay, welcome back. So today we're going to continue looking at resistors. We're going to look at some more complicated circuits than we did last time. But to review what we talked about last time, let's imagine we've got a voltage supply here, let's say 12 volts, connected to a resistor, let's say a 6 ohm resistor, and let's calculate what the current is going to be. Now first, we know that the current is going to come out of the power supply, but is it going to go to the left or the right? Remember, the long terminal of the power supply, that's the positive terminal. The current comes out of the positive terminal, goes around the circuit this way, and then back into the power supply that way. Okay, so the current, remember, comes out of the long side, the positive terminal, goes into the short side, the negative terminal. Let's figure out what that current is. Well, we know the relationship between the voltage, the current, and the resistance is Ohm's law, which is very important. Remember, very V equals Ri. Ohm's law is very important. So the current I will be equal to V over R, or 12 volts, divided by 6 ohms. So I equals 2 volts per ohm. What's a volt per ohm? Well, remember, if we put in SI units for all of our variables, then our answer will come out with the SI units for that particular term, and we know the SI units for current are amps. So amps, 2.00 amps. Now, what I'd like to do is to develop or talk about two general rules that will apply to all sorts of different circuits. Sometimes these rules might be a little bit difficult to see in microcircuits and things like that, but very, very often they still apply in all sorts of different circumstances, and they are called Kirchhoff's rules. There are two of them, and they are kind of the fundamental rules of circuit theory. So let's take a look at those. Okay, Kirchhoff's first rule is called the junction rule, or sometimes called the branch rule. And it states, the sum of the magnitudes of the currents directed into a junction equals the sum of the magnitudes of the currents directed out of a junction. Now this can be stated very simply in a form that I bet if I start it, you'll be able to finish it. It basically says, what goes in must come out. So the current that goes into a junction or a branch point, and I'll explain what that means in just a second. The current that goes into a junction must come out of a junction. It's basically another statement of the conservation of charge. Okay, a junction or a branch point is basically any place where wires are coming together. Now, if you have one wire going in and one wire coming out, that's not considered a junction. That's just basically, you can think of that as just a single continuous piece of wire. What we're talking about is either a place where we have a point where we have 3 wires or more coming out. Okay? So, what's the junction rule say? What goes in must come out in terms of currents. So let's imagine we've got a situation here where we've got 4 wires, say, connected to this point. And let's imagine we have 6 amps going in this way, and maybe 4 amps going in this way, and 7 amps going in this way. Is there anything that we can say about what's going on in this wire over here? Well, what's going in? We've got 6 amps and 4 amps going in, so we've got a total of 10 amps. Remember, an amp is a coulomb per second. That's telling us how much charge per second is going into this point. 10 coulombs every second are going into this point. Well, those coulombs are not building up at that point. They can't be stored at that point. They must be coming out of that point. Well, if we have 7 amps going up this way, we've got to have 10. We've got 10 going in. We must have 10 coming out. If 7 are going up this way, we must have 3 amps coming out that point. In other words, 6 plus 4, 10 going in, 7 plus 3, 10 coming out. Whatever goes in must come out. So we can add these together if they're numbers, or if they're just variables like I1, I2, I3, I4, we would have to have I1 plus I2 equal to I3 plus I4, or something like that. Okay, so that's Kirchhoff's branch rule. It has to do with currents. What goes in must come out. Second rule is called the loop rule. Okay, Kirchhoff's loop rule states, around any closed circuit loop, the sum of all of the potential changes equals 0. Again, we could restate this in a very simple term, which I bet if I started off, you'll be able to finish it. This basically states what goes up must come down. Now, that is in terms of the voltage changes, the potential changes around the circuit. So basically what this is saying, in terms of the voltages around a circuit, whatever increases in voltage we have, plus the decreases being negative, the positives plus the negatives must all equal 0 if it's a closed circuit loop, meaning if we go around a loop and come back to where we started. What goes up must come down. So let's take a look at some numbers here. Let's imagine you walk into a building, and it's a very tall building, and you walk in on the ground floor, and you walk up, let's say, 6 flights of stairs, and then you do something up there, and then you walk up 4 more flights of stairs, and you do something up there. Then you walk down, let's say, 7 flights of stairs, you do something there. What would you have to do in order to get back to the ground floor? How many flights of stairs would you have to come down, assuming all the flights of stairs are the same height? Well, if you go up 6 and then up 4, you've gone up a total of 10. If you come down 7, you'd have to come down 3 more to get to the ground floor. Whatever amount you go up has to be balanced by the amount you come down to get to where you started. In other words, around a closed loop. So 6 plus 4 minus 7, because you're coming down, that would be a decrease, minus 3 equals 0. So the total increases plus the decreases, negative decreases, must equal 0. Well, that's exactly what Kirchhoff's loop rule is telling us, but in terms of the electrical potential rather than, say, the gravitational potential. We could think of the height as the gravitational potential, and the changes in the gravitational potential must equal 0 if you have a closed loop, in other words, if you come back to where you started, in the same way that the sum of all the potential changes around a closed electrical circuit have to equal 0. Okay, so there are Kirchhoff's loop rules. Let's apply these now to some more complicated circuits than the ones we looked at last time. Okay, so here's a circuit a little bit more complicated than ones we've talked about before. We've got a single power supply, in this case let's say 15 volts, but now we have 2 resistors connected together, one 3 ohm and one 2 ohm. Now this particular way of connecting things together is called a series connection. In order for 2 things to be connected in series, they have to be connected with one end of one of them connected to one end of the other and nothing else coming out in between. So, these 2 are connected in series. If we had something else in here, another resistor, then they would no longer be connected in series. So, we have to have one connected directly to the other and nothing else coming in between. Alright, so let's get rid of that. Now, let's see if we can figure out what's the current in this circuit. Well, again, here's the high side of the power supply, low side, so the current is going to come out this way and go in that way, some current I. Now, notice that current is going to go up here, up here, up here. That is going to be the same current going through the 3 ohm resistor. There's nowhere else for that current to go. There are no branch points along the way, so we've got to have the same current going in. Likewise, that's going to be the same current going through the 2 ohm resistor. There's only one current through the entire circuit, and it's whatever that is, that current I. Now, let's apply the loop rule and see if we can figure out what that current is going to be. So, to apply the loop rule, we have to choose some point and go around a closed circuit around that loop. So, let's pick, let's say, this point here, and we will go around this clockwise. Now, clockwise, we're coming along this way. We are assuming, we're making the assumption that the wires in these circuits all are 0 have zero resistance, extremely low resistance relative to anything else. Now, if you'll remember the calculation that we did earlier when we looked at the resistance of a very, very long piece of copper wire, 100 meters long with a diameter of 1 millimeter, we found just a couple of ohms. So for any short wire, something you might use in a circuit in lab or something like that, or if you wanted to make something at home, probably you're going to use a much smaller wire, probably with a larger diameter. And so the resistance of that would probably be insignificant compared to any resistances that you might have in the circuit. So that's what we're going to assume. We're going to assume that the wires are basically resistanceless, or essentially negligible, have negligible resistance compared to anything else in the circuit. So, no change in potential, no change, no change. Now, we have to jump across the power supply. What's the change in the voltage? So delta V, let's see, I'm not sure if you can see that green on the screen, so I will switch to blue. Delta V is equal to, well, we're going from the low side of the power supply to the high side, so that's going to be a voltage increase, and it's an increase of 15 volts. There we go. Then we'll come along here, along here, along here. We jump across the resistor. Now, what's the voltage across the resistor? Well, we know for a resistor, V equals Ri. R is 3 ohms. I is I. We're trying to figure that out. But keep in mind now, we're going with the current. And current flows downhill. Ask yourself, does water flow uphill or downhill? Water flows downhill. In other words, from high potential to low potential. Electrical current does the same. Electrical current flows from high potential to low potential. So we're going from the high side of the resistor to the low side, so that's going to be a voltage decrease. So delta V will be minus Ri, in other words, minus 3 ohms times I. Then we come along, we jump across the 2 ohm. Again, we're going with the current, that's going to be a voltage decrease, Ri, so minus 2 ohms I. And then we get back to where we started. We've gone around a closed loop. All the sum of the changes in the voltage has to equal 0 according to Kirchhoff's loop rule. Well, there we go. So what do we have? We have 15 volts. We've got minus 3 ohms I, minus 2 ohms I. Well, we can combine those. That is minus 5 ohms I equals 0. Let's bring that to the other side, divide by 5 ohms, and we have I is equal to, 15 volts over 5 ohms. In other words, 15 over 5 is 3, and a volt per ohm is an amp. 3 amps. So what we have figured out is the current in this circuit is 3 amps. Excellent. Very, very good. Now, let's just imagine for a second, could we have made this circuit with the same voltage and the same current, but with only a single resistor? Well, could we have made a circuit that looks like this? Basically a 15-volt power supply, but connected to a single resistor that would give rise to the same current, 3 amps. What resistance could we put up there to give us the same response in the circuit? Well, we would know that V equals Ri, or R equals V over I. In other words, 15 volts divided by 3 amps, or 5 ohms. 5 ohms. We could make the same circuit and replace these two with a single resistance of 5 ohms. In other words, a 3 ohm and a 2 ohm resistor in the circuit, when they're connected in series, act exactly like a 5 ohm resistor. In other words, when we apply the same voltage, we would get the same current, whether we have a single resistor of 5 ohms or 2 resistors of 3 ohms and 2 ohms connected in series. This is called the equivalent resistance for these 2 resistors. When we connect them in series, the equivalent resistance of a 3 and a 2 is 5. Now let's take a look at this in a little bit more general fashion. rather than having specific values, let's just imagine we've got some general voltage V, some general resistances R1 and R2, and let's see what we get in that case. Okay, so here we have a series circuit, but now we'll assume we've got some general voltage V and general resistances R1 and R2. Again, we've got the current coming out going clockwise. Let's see if we can apply the loop rule and figure out the relationship between these. Well, again, we'll start here and go around the circuit. So, jump across the battery. We have a change in the voltage of an increase of V. Come around here, jump across R1. Again, going with the current, we will have a voltage decrease of Ri, in other words, minus R1I. Come along, jump across R2, minus R2I. And back to where we started, this must equal 0. So we have V minus R1I minus R2I. We can factor out an I from that and write that as R1 plus R2 times I equals 0. So bring that over there, divide by I, and we have V over I equals R1 plus R2. Now, notice that's exactly what we got. If we imagine again, we replace the single resistor, replace the two resistors with a single resistor in order to get the same current and the same voltage. V equals Ri, V equals Ri, V over I would equal R. That resistance would have to be R1 plus R2. The equivalent resistance of the two resistors in series is R1 plus R2. For this particular circuit, we'll call the equivalent resistance R sub S. In other words, the equivalent resistance for resistors in series. And what we find is that the equivalent resistance for resistors in series is equal to R1 plus R2. And you can just imagine if you were to put an R3 and an R4, R5, etc., what you could then do is basically just add R3 plus R4 plus etc. for as many resistors as you want. Essentially, the equivalent resistance of resistors in series is the sum of all of the individual resistors. R1 plus R2, etc. There we go. Excellent. Let's take a look at another circuit.